In this chapter, I'm going to show you how to linearly analyze the single load cases with the help of the linear analysis task. We already used this task previously, but now let's have a deeper look at it. If I open the task by double-clicking on it, we will find ourselves on the Load Cases tab, and if I make the window a little bit bigger, we will be able to see all the load cases in the database at the current status. We have the possibility to choose and select all the load cases to be calculated, or we select them manually, and here we select only the load cases that we really want to analyze. The position of this linear analysis task and when we perform this linear analysis task is very important. For example, when we have a linear analysis task after the execution of the construction stage manager, then we could also see the available construction stage manager load cases within this window as well. And if we calculate them accidentally by choosing all the load cases, then the results of these load cases that were coming from the construction stage manager would be overwritten and give very strange results. This is something that we really do not want, and therefore I'm suggesting you always to use the manually defined load cases to be calculated when you have construction stages in your model. And the way how you can control the load cases to be analyzed is simply first right-click on the first line, deactivate all the load cases, and then one by one or with multi-selection, you choose the load cases that you want to analyze. In this example file, we would like to analyze only the load cases that are assigned to a specific actions. For example, load case 3132, the wind load cases. Also, we would like to choose the settlement load cases from 51 to 53 that are assigned to action F. We do not want to analyze the single temperature load cases because those were just generated as a help load case. But we are very much interested in calculating the combined load cases from the single temperature load cases. Therefore, I'm choosing the load cases from 91 to 98. Load case 1 doesn't need to be selected the self-weight of the structure because this is going to be calculated automatically during the construction stages. As we activate a new part of the structure or a new element in the structure, its self-weight will be automatically calculated. Therefore, here we do not need to calculate this load case. The additional dead load, the surfacing, will be also applied in the construction stage manager. It's going to be activated not automatically. We are going to instruct the software in which construction stage the surfacing load should act. Similarly, the curvature loading from the pre-stressing will be automatically applied in the construction stage manager, so here we do not want to calculate it. Now let's move on to the Groups tab and explain the meaning of this tab in detail. The similar option of selection can be applied here as well. We can choose from the all of the group to be activated or only some of them or manually selected groups to be activated. When is this choice of selection is important? Let's imagine a case when, for example, in group 20, temporary supports to the structures are activated. And for the previously selected load case, I would like to deactivate these temporary supports and perform an analysis in this way. Review the results or further processing them. However, for another selection of load cases, I would like to perform the analysis with the temporary supports activated. In this case, of course, I need to select the group 20 to be active as well. This table also shows you the corresponding type of finite element that the group contains. We can see, for example, that in beam 10 and 20, we have defined beam elements, spring elements, and in group 20, we also specified some constraints. Now let's move to the next tab which is the Control Parameters tab. Below the Control Parameters tab, we can control the selected task. In this case, we can control the run of the linear analysis. For example, we can turn on or off special effects, such as in this case the warping torsion effect in the analysis. We can select, for example, the type of the solver that we would like to use in this linear analysis, choose or decide whether or not the coupling springs would keep its direction or not, and so on and so forth. And of course, there are more available possibilities or settings available via text input to control the analysis. The last two tabs, the text output and the graphical output, are available for most of the graphical tasks that can be seen in the SSD task tree. So what I am about to explain here about the text output tab and the graphical output tab can be applied to all other graphical tasks as well. The text output in this case refers to the output in the report browser. A certain task, such as the linear analysis task in this case, has many chapters in the report browser. The content volume of a chapter can be controlled here. For example, the output of the loads can be controlled if I select the drop-down list next to the loads and choose from the available options. I can select between no output at all regarding the loads, or I would like to get a normal output of the loads, a full output, or an extensive output. To have a better feeling what these options mean, you need to refer to the manual and see the echo options in the manual. To have a better feeling what these options mean, you need to open the corresponding manual, in this case the ASE manual, and search for the echo command. The echo command corresponds to the text output. So the description in the ASE manual in this case will give you a better overview and also a better understanding what an extensive output of the loads mean, for example. Normally, if we choose the default output for every chapter, then it is sufficient. However, sometimes you are looking for some extra output, and in this case, you need to know and remember, and it can be set via the text output tab or via the usage of the echo command. Below the graphical output, you can also control the type of output of the report browser. It means that by default, the software will implement some pictures, or we should say graphics, in the report browser output. Now you can see on the screen, for example, the default graphics that are going to be printed into the report browser. If you do not satisfy with it, simply you can open or close a chapter and select graphics that you would like to incorporate in the report. If you move your mouse to the bottom left corner, you will reach the Scale chapter, where you can set the scale of these graphics. It is possible to choose the Scale to Fit option or the Engineering Scale. If you choose the Engineering Scale, the software will try to select from the below scales, which are most commonly used in the engineering practice. If you choose the Scale to Fit, then it might happen that the scale will be, for example, 1 to 143, which is not really necessary an engineering scale. You can also set the page format to be portrait or landscape. You can also set how many pictures you would like to see per page, 1 or 2. You can select and set the font size and the graphics. And you can modify or define the view of the structure. By default, the software will choose a standard 3D view, but if you prefer, you can have your view from the XY plane, the XZ plane, or the YZ plane. Furthermore, you can create a user-defined view, and set the exact view that you would like to see in the graphics. If you want to set back the settings to the default ones, then you need to click on this button, Default Settings. If you finished with all the settings and you want to process this task at the moment, then you need to check in the Process Immediately button and click on the OK. Now the task will be performed. We can see that module ASE was performed and module WinGraf was performed. The second module was executed because we have chosen to present graphics in the report browser. If we didn't select any graphics to be plotted in the report browser, then only module ASE would have been executed. Now we can see that both of the tasks have been run without any errors and without any warnings, which is fine. Now the results are available for representation, and this is exactly what we are going to do in the next chapter. See the results in detail. In this chapter, I'm going to introduce you the system visualization, or so-called Animator. Currently, I'm working on the model called ptc_bridge.sofistic, which can be found on your desktop in the subfolder named ptc bridge. However, this model file can also be found in the corresponding model file folder of this chapter. So after having run the linear analysis task, the system visualization will be automatically activated. But we can also find a system visualization ribbon at the top. Now I'm going to guide you through the possibilities and all the settings of this system visualization ribbon. First and foremost, the previous name of the system visualization was Animator. So if you hear me saying Animator, sorry for that, I want to say system visualization instead. Since this ribbon is all about the system, first we see the system itself without any animation. However, if we click, for example, on the first load case, the self-weight, we will see that the structure starts to animate. At this point, we can start to use the cursor keys on our keyboard to go through the already calculated load cases. For example, now we are looking at the additional dead load, previously the self-weight. However, please notice that the magnitude of the deformation for the self-weight and for the additional dead load is exactly the same. This is because the software factorized the deformation of the load cases to be equal with each other and to present a nice overview of the deformations. We can see the magnitude of the deformation of the certain load cases grayed out at the amplitude line. For load case 2, the magnitude of the deformation is 964, whereas for the self-weight is only 154. So a better way of representing the results and compare the deformations is to stop the animation and set up a common magnitude for the deformations. You can do that simply clicking on this freeze image button and the animation will stop. Then as the next step, you need to click the amplitude checkbox and set an explicit value either by using the slider or simply entering a value here, for example, 150. If now we click through the individual load cases, the deformations will be really comparable visually. For example, now we can see that the self-weight makes much more deflections to the structure than the additional dead load, which is reasonable. So now we can go through the individual load cases, either by using our cursor buttons or simply select one with our mouse. But there is also a third option, namely to use the first, previous or next buttons in the top left corner. This procedure is the primary review of the results, which I suggest you to do at the very beginning of your project. Since later on, when you have more complex load cases and more complex effects, you need to be sure that the structure is working properly for the single load cases. After having went through the individual load cases, I would like to show you the next feature in the system visualization, which is the information about the elements. You can receive information about the finite elements if you simply double click on one, and then, as you can see, automatically the next tab was activated and the software shows us the information of the selected element. In this case, for example, the element is with the number 200017. From the settings of the group divisor, we know that means that this element belongs to group 20, and since the group divisor was set to 10,000, this is the element number 17. This is the reason why we can see a 6-digit beam ID here. However, we can also obtain information about the used cross-section in this beam element. We can also see the number of the structural line on which this beam element was created. We can see the group number, the material number of this beam element, and we can also see the first and the beginning nodes of this beam element. Even we can see the beam forces of this beam element from the selected load case number 1. The information of the elements can be achieved either by double-clicking or using this element info button. You have the possibility to turn on and off groups for better visualization. For this purpose, you need to click on this groups button, and then a new dialog box will appear. In this dialog box, you can use your right mouse button to uncheck all the settings, for example, or select all the elements. But of course, you can select by clicking simply the checkbox. For example, if I now click on the OK button, only group 10 will be presented on the screen. You also have the possibility to take over the settings from graphics, in other words from WinGraf. This is something that I'm going to show you later on when we are discussing WinGraf settings. Now I'm going to set back all the groups to be visualized and click on the OK button. With the Hide Group button, you can hide some of the groups. For example, if I click on the button and then click on the superstructure, then group 10, the superstructure, will be deactivated. If I want to show the hidden elements again, I just need to click on this button to show the hidden elements. If I click on the Hide an Element button, then only one or more elements will be deselected or deactivated according to my clicks. Sometimes this representation can be useful. For example, here if we zoom in to see, and once again the hidden elements will be shown if I click on the Show Hidden Elements button. With the zoom button, I can simply select or make a fence with my mouse, and the selected part of the structure will be presented in a bigger scale. If I want to show or present the structure again in the full view, I just need to click on the border zoom button. However, a very good zooming and zoom extent option can be achieved by scrolling the middle mouse button, and you can also zoom in the part of the structure that you would really like to represent. Combining this with the dragging when you push your middle mouse button makes the zoom and the zoom border buttons very rarely used. With the help of the next few buttons, you can set the view of your structure. You can have an overview about the XY view or the XY plane, similarly about the XZ, the YZ plane. Of course, here you can also zoom in with your middle mouse button. And you can represent your structure in a 3D view or a perspective view. Sometimes the representation of the support and the hinges in the structure seems to be a little bit too big. If you want, you can absolutely turn off the supports or the hinges by clicking on the supports and hinges button. Back and forth, you can turn on and off the hinges and the supports. With the help of the coloring results button, you can simply turn on and off the results that can be visualized or can be seen on the left side of the screen. And with the button on the right side, you can influence what results to be shown. By default, the utilization of the elements is presented. But you can change this if you click on the arrow button and choose, for example, the stresses to be presented or the von Mises stresses. You can switch between the results simply clicking on this button many times. And now you will be directed back to the utilization. It's very important to emphasize here that these utilization stresses or von Mises stresses are just for primary overview of these results. They are simply calculated with the formulae N over A plus M over W. Still, it is a quite handy tool to view and double-check the utilization or the stresses within the structure. On the other hand, the sum of the reaction forces in the global X, Y, and Z direction is calculated very precisely, which gives you another opportunity to double-check the loading and the output. With the Mesh Lines button, simply you can turn on and off the finite element mesh of the structure. With the cross-section, you can turn on or off or partially turn on the visualization of the cross-section. So you can choose the no cross-section visualization at all, or you can select the only quad cross-section. If you have beam elements, then it's going to show you the perimeter of the cross-section, or I would say rather the contour of the cross-section. And when you choose the full visualization of the cross-section, then you will see the cross-section fully visualized. You can cycle through the options by simply clicking on the cross-sections button many times. There is also the possibility to represent the coordinate system of the structure. If you drop down the menu, you can choose the local coordinate system representation, and if we zoom in, we will really see the local X presented with red, then the local Y presented with green, and the local Z presented with blue colors. As soon as I clicked on the representation of the local coordinate system, of course the representation of the cross sections has been changed. We can also choose to show the global coordinate system. In this case, if we present the global structure, then we can see the directions of the global X, global Y, and global Z axis. So to wrap up, the system visualization is a very good tool to have primary overview of the results after having run the linear analysis task. In the next chapter, I'm going to show you the results of the result sets from the single load cases. In this chapter, I would like to show you the results of the result sets from the primary load cases. I'm working on the modeled code ptc_bridge.sofistik, which can be found on your desktop in the subfolder named ptc_bridge. However, this model file can also be found in the corresponding model file folder of this chapter. To show or to represent the results of the R sets from the single load cases, or we can say primary load cases, I have set up a so-called interactive graphics in SSD. I will show you how to create or set up such an interactive list and graphics later in the course. For the time being, I will only explain that once you have created an interactive graphic, you need to run the task like any other graphical task. So from the drop-down list, I will choose the calculate RSet results of single load cases. And now we can see that in the background module results was performed. Again, we didn't receive any warnings and errors, so everything is fine. So now we just simply open the report browser of this task by simply choosing the reports from the drop-down list, and then the result viewer will be open. How you can work in the report browser will be explained in more detail later on in our course. For now, I would like to show you that I have set up 6 chapters. One chapter to represent the results of the result set up at support 1 axis on the left, support 1 axis on the right, support 2 2 axes on the left, support 2 axes on the right, and so on and so forth. So if we look at, for example, the first table, we can find in the first column the individual or single load cases. Also, we can read the corresponding load case titles, which helps us to be oriented. Then in the forthcoming columns, we can see the internal forces of the result set. For example, in the first column, we can see the spring force in spring number 200,101. The second column stores the spring force of spring number 200,102. The third column shows the spring force in spring 200,103. The fourth column shows the deflection of spring 200,101. The seventh column, Vx, shows the rotation of spring 200,104, and so on and so forth. And finally, the last column shows the rotation of the spring 200,106. Also, you can see how useful it is to use titles when we set up the result set, because now we can be sure that these results are for the support at the first axis on the left side. Also, these tables give you a good overview about the results of the result sets. We can use it for quick checks to see if a bearing is working as we expected. Let's see, for example, the first supporting line, and we can see that on the left side we have a bearing that cannot move in the global y direction. So if we now, for example, look at the effects from the wind load in the global y direction, we will see that we have really reaction forces due to the wind, which is good. If we now look at the first support line, the bearing on the right side, we will find no value as reaction, which is again correct because this bearing can move in the longitudinal and in the transverse direction as well. Similarly, if we review the deflection or deformations of the left bearing at the second support line, we shouldn't find any displacement in the global x or global y direction since it is a fixed bearing. Let's see if this is the case. I will scroll down the table, and now on the second page I will find the support at the second support line on the left. And really the deformation in the global x and global y direction from the temperature changes are equal with 0. With similar checks you can prove the functionality of the bearings at any axis. After having done these verifications, I would like to show you a third way or a third tool to double check the initial results from the primary load cases in the next chapter. In this chapter, I would like to show you a third way to double check the results of the primary load cases. I'm working on the model called ptc_bridge.sofistic, which can be found on your desktop in the subfolder named ptc_bridge. However, this model file can also be found in the corresponding model file folder of this chapter. I'm going to insert two new graphical tasks, the so-called interactive graphics, to demonstrate the results in graphical format, which could be the third way to double check the results from the single load cases. I have inserted two new interactive graphics into the SSD task tree to demonstrate this. The first interactive graphic will show you MY bending moment diagrams of the temperature load cases and from the settlement load cases. Similarly, the second interactive graphic will represent shear force diagrams in the local Z direction of the beams from the temperature load cases and from the settlement load cases. We will cover how to create such an interactive graphic later on in our course. And now I would like to simply just calculate this interactive graphic task and then with the right mouse button open up with the report browser. If we open the report browser, then we can find 5 pages. On the first page we can see the bending moment My from load case 51, which was the settlement at the first abutment. Then in the first page, in the second picture, we can find the bending moment My diagram of load case 52, then in the last one 53. On the forthcoming pages, I'm presenting the My bending moment diagram from load case 91 and 92, and so on and so forth. For example, here 95 and 96 as well. So these graphics can give you, again, a very nice overview about the single load cases if everything is fine and your model is working according to your expectations. If we now close back the report browser and run the second interactive task and then open up with the report browser again, we are going to see the shear force diagram of different load cases. On the first page, we can see the shear force in local Z direction from load case 51, then from 52 and 53, and similarly we can review the shear force diagram from the temperature changes in load case 91, 92 for example, or 95 and 96. So the purpose of this demonstration was to show you how you can double check the primary results of the single load cases. We have learned that basically we can use the system visualization task first to have a first overview about the behavior of the structure. Then we can go ahead and we can create interactive lists or interactive graphics to double check the results. This concludes the current chapter, and now we can continue with the definition of the traffic loads in the next chapter.